well, you can also ask things that are not mathematical. You can ask, for instance, career advice is a good thing. Or the situation of research groups in Brazil about this subject, for instance, is also. You can ask anything you are curious about, okay? And well, and anything includes anything. Always somebody asks, what's the meaning of life, or some jokes. Jokes are allowed also, okay? But please, not only jokes, okay? So, and this I will distribute. That will be this small pieces of paper here. You can write your question, and you can write it actually in any piece of paper. But this is beautiful. I have a small dragon on it. So, and you put the questions into boxes. There will be one box here, just outside the auditorium. And there will be a small dragon, so it's the correct box. And then there will be another box in the computer lab, okay? So try to write down your questions until 5 or 5:30 so that I can organize more or less the sequence of questions, okay? Is that okay? Yeah, everybody got it. So, Renato, it's up to you.
Hi, good morning, everyone. Okay. So, how are you doing? Tired already? It's only Thursday yet, right? So, you're kind of half point yet, right? Okay. Right now, I think it's time to go back to the exercise we left behind, or what? Did anyone try to do that again, or? No time for that. Okay, do you want to see the solution? Or do you want more time to try? Okay, now let's go for the solution then, right? So, okay. So this is, I didn't open it here. I think I didn't share the other one. Let me see. So this is, well, where are the solutions, right? Where are the solutions? No. Well, let's just open a new notebook, okay? So these are the exercises over here. Okay. No. Oh, okay, no, this is this one, and it's this one, the exercise. Okay. So here it is, the exercises, okay? And I think we had solved already this model here, but I just do it again, right? Because I couldn't quite find where it is over here. It should be somewhere, but I don't find solutions anywhere here. This guy here doesn't have the solutions, right? Okay, no solutions. Okay, so we just do it again, right? So no worries. Okay, so I'll take this guy here, this SIRS model, and I will just let me create a copy here. Although this is my notebook, right? But even then, okay. So this is now solutions. Okay, so the first part. To get this prevalence versus incidence here, first I have to have the model itself, right? So let's just do this again. So I'll change this for SEIRS, and I have a new mu parameter that I'm going to to say that it's 1/4. I think everything else is the same, right? So 2, 1, 1 over 12, 10 to the 6. Yeah, everything else is the same. And now I have a new equation here for, oops. So this, yeah, I have x2 here. You remember this kind of, right? Yeah, from several days ago, yeah? So this is going to be x2. This is going to be x2. Okay, and this is now the same stuff here, over here, okay? But with a plus. And then minus mu times x1, comma, and this, instead of this, there is the exposed becoming mu times x1 minus gamma x2, okay? And hopefully this works, yeah, cleanly. Let's see. I forgot to ask, is it easy to read and everything? Yes, maybe. Yeah, of course I forgot something here that is, I changed the name and didn't change it here, and also the parameter mu is missing here, right? So yeah, here it is. And mu now is not defined. Ah, well, that's funny. Oh. Initial condition, right? So yeah. So okay, and now a little bit longer time. Okay, and now we're done. Okay. Well, I think my performance last time was a little bit better, but I was in a bit less of a hurry, right? So okay. Okay, so we have the solutions here, and now the question is, okay, how do we count new cases? Right? This is the issue, right? And remember, for SAIFR, we could just use S. Why was that, right? So let me go back a little bit to that model, okay, to the SAIFR, right? I think it's in the very first notebook, right? So we're kind of slow today. The very first notebook that we had, it's this one, right? So so here, what is it about the susceptibles in this model, right? The thing is, for susceptibles in this model, the only change in the number of susceptibles is due to new cases, okay? So what we want to do is just introduce a new variable whose only change is due to new cases, okay? Yeah, so let's go back here. These are the solutions, right? So I just copy and paste this stuff here over here for exercise 2, okay? And now I will add a new equation in the end, okay? And what are new cases for this model, right? So usually you count cases when people start having symptoms, okay? So exposed individuals probably are not symptomatic yet, so they're not cases yet, right? So they won't be counted as ACEs yet. They will only be cases, they will only be registered as ACEs once you have the onset of symptoms. So once they go from the compartment E to the compartment I. Yeah? Okay, so what is the rate of new cases? Is the rate of people going from the E class to the I class. Yes? And this rate is this one here. It's the mu times E. Yeah? This is the rate of new cases. Okay? Okay, so with that, I can go here and I say, well, I will have a new equation here that is just mu times this guy here, x1, that is E, right? Mu times x1, okay? And now I start with zero cases, right? So what I did essentially was taking these equations here, let me copy and paste them, right? So in these equations here, okay? And let me write a new cell down here, here. And I added to these equations here a new equation that is, let me call this C, right, for ACEs. So, yeah. that is just mu times E, and this is C, okay? So these are our new set of equations, right? So I have now this new variable here whose only job is counting the accumulation of new cases. Yeah? Okay? Okay, and now, with that, I have to introduce a new initial condition here, and now I have this new guy here that is number of new cases, that is C, okay? And you see that C is just increasing, right? So, yeah, so let me plot, instead of plotting it like this, let me forget about this plot for now, and let me plot just new cases, okay? So this is time, X, this is the fifth column, right? So this is new cases, okay? You see, it's always increasing, right? I think it's more useful to see this as a proportion of total population, right? Why is it always increasing? Because, sorry? You're, sorry? Oh, there's something wrong here, right? Yeah, this is accumulated cases, exactly, right? But it shouldn't. Yeah, let me do something here. Let me go back to this plot here. This is funny, right? So I have to exclude the last one, right? So up to excluding -1. So at the end here, yeah, of course. At the end, okay, because this is endemic, yeah? So at the end, even if the populations are stable here, you see that you keep getting new cases. You keep having people being exposed and infectious, yeah? So you always keep getting new cases all the time because this is endemic, yeah? Okay, people? Yeah? So you keep accumulating more and more cases. But since this is a constant, then after some time here, after, I don't know, 125 more or less, this rate of new cases becomes a constant, and then your accumulated cases grow linearly. Yeah? Okay, so let me plot only this one again, and to see if we got this right. Yeah? So more or less around here, 125, and so on, this becomes linear, yeah? So this is accumulated cases. To go from accumulated cases back to new cases, I just have to do exactly what I did with successuals last time. I just have to take the difference from one day to the next, or from 1 week to the next, and so on, yeah? And this is, once again, since I'm, since I'm being a little bit, I'm committed to reusing all codes that I have ever written, right? So I will copy and paste, even if I take 10 minutes to find the old code. Okay, I will find it, okay? And then this is in the addendum down here, yeah? Yeah. Yeah, this is addendum. There's a version in R of these tutorials, okay? For people that like to code in R, the first 2 tutorials have versions in R, okay? I added it to the end. But here it is, the code for, yeah, is this stuff here, right? So I take the number of days here, and I will use this guy here, okay? So, yeah. So instead of having this, let me write a new cell down here. So this goes up to 200, right? So let's take weekly cases. How about that? Weeks, not days. Weeks. And then, so C weekly is going to be S. Now I have to take the last column, okay? And here is weeks, okay? And then I can plot this. Weeks, week, okay? Oh, no, I missed some stuff, right? So I have to do this stuff yet, okay? Yeah, now it's going to work. This is just the cumulative number of cases at each week, and then the delta of this, so the number of new cases is going to be C week -1 minus C week 1. Yes. Oh, and this is reversed sign right now, right? Because remember that number of nucleases, it was the opposite of susceptibles, right? When susceptibles lost someone, it's a positive number of nucleases. Now I have cumulative cases, so I have to do the opposite sign, okay? And now I plot this. This guy here, this vector, has one less element than number of weeks, so I start with the second week, okay? So this is stuff here, okay? Yeah, and this is number of nucleases as a function of time, okay? But this is, you see that even for it goes up to 200, right? So, but the numbers are actually, if I plot this with dots, you see that this is not every day, it's every week, right? It's at each 7 days, okay? Yes? Yeah, you would. Yeah. There's a function in Python that does exactly what I wrote here. That is called a diff. Yeah, it does the same thing. You can. Yeah. That instead of this stuff here, I would have written this as. Yeah, this is the question. Yeah, this is the same. Okay. More questions. Is it clear? Yeah, easy. After you saw the answer, then it becomes very, very simple, yeah? Sorry, you have to do this, you have to remove, here. Here or there? In the plot, in the plot. So this is, it does make a difference because it kind of shifts the scale of the x-axis, okay? But usually it makes sense to lose the first one, not the last one, right? Because you are looking at accumulated cases at day 0 and at day 7. And this is the number of cases up until day 7, right? So it's more useful, almost to plot this as cases we index it at the number 7, at the day 7, not the day 0, you know, because they're not. It's funny to plot new cases that will come in the following week. Usually you plot the number of the week, the cases that happened during the previous week. Yeah. Or sometimes you just put the number of the week instead of plotting days. Okay. But yeah. More questions. Okay, so this is really practical, okay, because you can do this for any kind of model, right? Any kind of model, and count, you can count cases in this way. So for instance, if you have a model that has severe cases or that has deaths, for instance, okay? Severe cases like hospitalization, you just count the number of people that enters the hospitalization class, and then you can compute the number of new hospitalizations that your model yields, for instance, okay? So you can do this for any kind of, any class in your model. You can even count several different new occurrences per day or per week and so on, right? So new total cases, new hospitalizations, new deaths, new, you know, whatever you want. You just have to know the rate with which these cases arrive, yeah? Okay? Okay. Good. Okay, so let's go for today's topic. Okay, so today's topic is, I hope, very exciting. It's we are finally talk a little bit about data. Okay, about fitting models and so on. So the link to this notebook is already today's notebook is already here. Okay, so you go there. Is this last 4. And it's this guy here, okay? Okay. Let's see. So okay, today, at the same time, that is really, really interesting. I hope it is for you as well, right? So it's also very, very tricky working with data, and especially fitting models to data. Okay, it's not a simple task at all, and the tools for that and the state of the art of this is actually very complicated, right? I'm not going to tell you otherwise, right? So what I'm going to do here is tell you about some very simple, very basic stuff that is not the state of the art, okay? So if you do this, you have to be aware that there are limitations, and there are not limitations like when you write your paper and you have to write something like, there are some limitations there, but you don't care about them. No, these are serious limitations that really impact what you're doing, okay? So it's not something to throw under the rug and so on, right? So what I'm telling you is that, okay, this is not, like to do this in a more professional way, you have to go quite a bit further, you know? Not this tutorial here, unfortunately, is not enough, but it's what fits in 1 hour of discussion, okay? So, so let's start, okay? So the idea is, okay, you have a model that represents somehow the processes you want to include in your model and so on, okay? And then you want to fit the model to a set, a time series, for instance. So you have an epidemic, and you have the curve of, I don't know, prevalence or new cases, incidence, and so on and so on. And you want to, what does it mean to fit the model to the data, okay? What it means is you want to find the parameters of your data, or of your model, that best represent, or that makes your model approximate better the data, yeah? Does that make sense? Yeah, so what you're fitting is not the data, you're fitting the model to the data, you see? So the data is fixed, okay? Okay. Okay, so far so good. So, so there are going to be errors, okay? That means, what I mean by errors here, your model will never ever, it's impossible to get your data to exactly reproduce the data, okay? That's impossible. So there are going to be differences between your model output and the data you have, sure. But then what are the possible origins for these differences? What are possible differences? From where those differences come from? Do you have guesses? I'm pretty sure you know something about this, okay? So speak up. Sorry? Measurement. Yeah, measurement error. Okay, so like, well, if I'm talking, for instance, of an epidemic, of course, it's impossible to really count all of the cases. You're going to miss some of them, so some of them will go unreported, and so on, or misdiagnose it, or whatever. Okay, so measurement error. Okay, what else? Sorry? Can't hear you. Systematic error. What is a systematic error? Experimental design errors. But this is not an experiment. Okay? If you're talking about an epidemic time series, this is no experiment. Oh, I hope not, right? Yeah? Okay. Sorry? The test is not, what do you mean? But the test is not correct. What test you're talking about? Sorry? Oh, I'm sorry, people. I'm too much heavy metal in my, yeah, it's my ears are young, okay? So the test you use to confirm a case. So this is kind of included in measurement error, right? So if you have a test that is not very accurate, or it's not very sensitive for the thing you want to measure, like well, we had in COVID, right? So a lot of tests that people clearly had COVID, but the test was negative, right? But this is kind of inside measurement error, right? You're not able to measure accurately the number of cases, but this is already covered in measurement error, I guess, right? So yes. Yes. Okay, so you're saying that the processes we're talking about, like contagion and so on, infection, they are stochastic. So like if you could run back in time and things were a little bit different, perhaps the epidemic curves would be a little bit different. Yeah, that's what you're saying. So reality is complicated, and stuff are like those processes that we are modeling as ordinary differential equations that are deterministic, like with the same parameters, with the same initial conditions, you always get exactly the same solutions. Real life is more complicated than that, right? So we expect to have variability in this process, right? So it's kind of, well, maybe I run into someone, and then if I didn't run into that person, I wouldn't get infected. And so the process of infection itself is stochastic, it's not deterministic, right? So it could have a different trajectory, a different data in a slightly different setting, yeah? Okay, what else? Okay, you're saying, sure, for instance, I'm thinking of epidemic time series. You're like, well, your model fits the initial phase very well, but then later on, it kind of gets messed up, okay? So, but how could that come about? What is, okay, you're telling kind of the symptom. I want to diagnose this, right? How could your model fit well the first part of the data and not the last part of the data? From where does this difference come? Yeah, so the process is different. So if you have a difference in process, what does this tell us about? That our model is missing something, right? This is a possibility also, yeah? Yeah? It's a possibility. So a strong possibility is also that your model doesn't account for everything, okay? So our models, they may be nice and so on, but maybe they don't account for something that is missing, and then things are wrong, yeah? Okay, so this is also possible, yeah? So yeah, I have a difference between the real processes and the process we are describing in our models, okay? But let me ask you a question, right? So have someone ever written a model that took into account all the processes in reality? No, right? It is impossible, right? So to get something that is as complex as reality, you need reality itself, okay? So it's too complicated. So no model is actually complete, right? In the sense of fully describing all of the processes in reality, right? So our models, in a sense, they're always incomplete, okay? So how do you, so if our models, in a word, right, we can say that all models, in a sense, are wrong. Of course, there's a famous phrase of all models are wrong, but some of them are useful, yeah? So the thing is, how can we fit models to data, knowing that our models cannot possibly represent all processes, yes? How can that be, right? So the point is, well, maybe these differences, they are not so large, okay? And on average, the processes we are leaving outside of our model, that we're not including in our model, if they don't have a strong bias, right? You are not always under or overestimating, right? You see? If on average, these processes kind of don't make too much of a difference, then your model may perform reasonably well. Yeah? Does that make sense? Yeah? So in a sense, it's stuff that is not included in your model ends up, you can think about this pretty much in the way that he was talking about. You can think of this as noise in the process, but this not noise is not intrinsic noise. This noise doesn't come from, I don't know, quantum mechanical fluctuations and fundamental randomness and so on. It's just stuff that happens that your model doesn't account for. And this is like sometimes you predict a certain rate of infection, and sometimes your model is going to say to shoot higher or lower due to not intrinsic variability, but variability in stuff that your model doesn't account for. Yeah? So this is what is all process noise. Okay? It's a noise that is due to process. Okay? But again, it's not intrinsic noise necessarily. It's just noise in stuff that your model doesn't include. Okay? Yeah, so these are the two main types of error, right? So of course, in going to many details like measurement errors, there are many sources of measurement errors. Process errors, also there are many sources of process errors. Okay, so mostly stuff that is in your model. Okay, so now I want to do something very, very simple. Okay, so what I'm going to do here is I'm going to completely ignore noise due to process, okay? Completely ignore that, okay? Why? Because I'll tell you at the end, but it's more complicated to include this. It's not impossible, it's just more complicated, okay? So I'm going to go with, well, what if our model is perfect, is completely a full description of reality, and I assume that all of the noise comes from measurement errors, okay? So this is the idea behind this stuff that is least squares, okay? So least squares is like this. So I'm pretty sure that most of you have seen something like this before, least squares fitting, or yeah, or also I will generalize later on to maximum likelihood, okay? So either one of those maybe you heard about, but let's go quickly over this, okay? So because it's important to get the fundamentals right. Oof. Okay. Okay, so let me, instead of showing all this stuff here, let me just plot some curve here, okay? So what I do here is I take values of x from 0 to 10 here, and then I just say that y, on the y-axis here, is just some linear function of x plus some random noise, okay? So plus some random noise. This generates random numbers with a normal distribution, a Gaussian distribution, with a variance of 2, okay? Okay, and when I plot x against y, well, this is a linear relationship, right? So this looks like a linear relationship, yeah? Sure? So I'm not talking yet about epidemics. I'm just talking about a relationship between x and y. Okay? How do I, here I know that it's a linear relationship, okay? Because I just generated this data, right? But what I want to do is I want to fit a straight line to this, okay? I want to, if I didn't have these parameters here, this 3.5 and this 0.2 here, okay? These are the parameters of my model. I will have to find out. How do I find out? Okay, so I define a function. Okay, I define a function, and then I okay, so let me. Yeah, I define a function that receives the x data, okay, the values of x, and the parameters of my model, and then I return the y values. Okay, so these are the y values: a times x plus b. Okay, because this is the equation for a straight line, okay? And then I use, in SciPy, we have this function called curve fit. That is a very, this from SciPy optimizing imports curve fit. And this is a very simple function that does least squares, okay? But before I talk a bit further about this, I just want to tell you what does fitting means here, okay? So what I'm looking for is, I'm looking for a line, okay, a line that, what does it have to do exactly, okay? Well, I want it to be as close to the points as it can, right? Okay, so there may be several ways of doing that, right? So if I try to minimize the mean value of this distance, or the median value of the distance between the points in the line, or there would be several different ways of choosing what to minimize, yeah? But the main stuff, the stuff that people usually do is do least squares fitting. What is least squares fitting? I take the difference at each point, the difference between the line and the point, right? And take the square of this value, okay? And then I do this for each of the points, okay? And then I sum all of this together, okay? And this will give me a number, and I want to minimize this number, okay? So this is least squares fitting, okay? I'm trying to minimizing the sum of the squares of the difference between your model predictions, the orange line, and the blue line, okay? So this is what this error function here was that I wrote here, right? So I just take f, that is my model, that is the line over there, minus the data point at each I, you see f of xi, minus yi. I take the square of this, I sum the values over all of the points, and this R here is a number that I want to choose A and B, the parameters of the model, so that this is as small as possible. Okay, so this is the mechanics of least squares fitting. Okay, and I won't go into, well, how does this nerve fit internally finds this best model, these values of A and B, and so on. Okay, this is more technical. This is optimization algorithms and so on that I won't go into. Okay, so far so good, people. Does the mechanic of this, yeah, and it makes sense. Okay, it makes sense, right? Do you agree with that? It makes sense to do this to find the best line in a sense. Yeah, but why this square? Couldn't I just sum it, the absolute value or the fourth power, or I don't know, something else? Why not? Right? I could. Yeah, it's possible to do that. Okay? But usually I take least squares fitting because it is related to an assumption that is, you see, this data here, I generated this data from assuming I generated the data from a straight line plus a measurement error. Yeah, so you have to look at this stuff here, okay? And you have to think of each point here is like the point is here, but there's a normal distribution around this point. You see, in the y-axis, there's a normal distribution. Yeah, and this is the model of the errors. Yeah. The model of the errors, you use a kind of statistical model to how the errors of measurements are distributed. Okay, so if you assume a Gaussian, then you arrive the normal distribution for these errors. You kind of arrive at this is Earth fitting. Why? Okay, so this is let's stop here. Okay, so yeah, I will add. I have some questions for you to try to answer later, okay? But I won't go into this right away, okay? Well, maybe this one is interesting. Just a moment. Let's just look at this for a moment, okay? So here we know that we generated the model exactly in the way that we are fitting. Okay? I know that the points are just a line plus random noise, normal random noise. So should we over the exact same values that you included or not? Not necessarily, right? So here I had 3.5 and minus 0.2, and the parameters that I get from here are 3.48, 0.2 positive, not negative. Yeah, so you see that you don't necessarily over exactly the same parameters, because the parameters we find, the efficiency we find from this fitting is also subject to some variation, okay? Yeah? So we get an estimate, and from the covariance matrix, right? So this is how variable this these estimates are, you can get some idea of how variable or how much to trust this parameter. So usually here in the main diagonal, I have this is kind of the variance of the first parameter and the variance of the second parameter. So if I take the square root of this is 0.1. So it means that my coefficient here is very probably between 3.4 and 3.6. Yeah, and this is okay. And the square root of 0.3 is what? It's 0.6, right? Yeah, 0.34, it's close to 0.6. It means that my parameter, my second parameter is probably between minus 0.4 and 0.8. So there's a bit more variability here in the second parameter. You see? So these are just a rule of thumb, okay? And this off diagonal terms, this matrix is symmetric, okay? This tells me how changing one parameter affects the other, right? So this negative value here means that if I increase the second parameter, I should decrease the first parameter and vice versa, yeah? And this is more or less easy to see on this straight line because, you see, if I increase where the line starts, I just make it go up a little bit, okay? To fit more close to the points, I have to decrease the inclination a little bit, yeah? Does that make sense? Yeah, so they are anti-correlated, okay? When one increases, the other has to decrease a little bit, okay? Okay, so back to model assumptions, okay? So where does least squares come from? It comes from this general method that is called that it's called the maximum likelihood. So what is a likelihood? Okay, so everyone kind of knows. I really mean kind of knows, right? Because it's actually complicated. But everyone kind of knows what is a probability, right? Yeah, what is a probability? Great. But then what we are trying to do here is, well, I have data. I have data points. I have a model, and I have parameters for this model that I want to somehow fit to the data. Okay. What we are looking for now is, okay, if I have the model, I say I have a value of A and B, okay? I can calculate something that is, what is the probability of some values of Y? Okay, if I have A and B and a model for the noise, I can calculate this. Okay, I go, how do I do that? How do I calculate the probability of some set of points? I take if I have the values of A and B here, I go, okay, the probability of finding some points here is, okay, my model prediction is here, and I put a normal distribution around this point, and then the probability is just the probability of drawing a normal with that value, with that distance from the orange line. Yes? Okay, so each of these points, actually, I can attribute a probability. Yeah, a probability. So what is the probability of ours? You see, these points that are very close to the orange line, they have higher probability than the points that are farther apart. Yeah? So these are kind of low probability, and these are high probability. Yeah? Okay? But this is kind of funny, right? Because, well, we have already observed the points, right? So it's not really a probability, okay? So, yeah, it's kind of, yeah, because you're not, like, if I say my model is true, and then I can ask, what is the probability of drawing some value for the model, yeah? But now I'm doing it the other way around. I have already observed the data, and I want to tell, after the fact, what would be the probability of having observed that point. You see? Yeah, so this funny concept, this is the likelihood, okay? This is the probability, the likelihood of a model given a data set is the probability of observing that data set given your set of parameters. Does that make sense? Or not? It's kind of it's not so simple, right? I have to do some, yeah, because it's not probability, but it's somehow related, okay? Yeah? Come on, questions? Or is it too much too fast? I don't know. Or everyone is pretty familiar with that. I'm saying stuff that everybody already knows, and you're just saying, yeah, 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 sure. Oh no? I don't know. Tell me. Yeah. Okay. Let's move on then. Okay. So if you do this calculation for the normal distribution, what is the equation for normal distribution? It is just the exponential of minus x squared, where x here is the difference between the predicted value and the observed value. Okay. And this is it, right? So the first, there's something that is very important here is I have a data set, so I don't have a single point. I have several points, okay? What are the probabilities of observing this point, and then this point, and then this point, and then this point, and so on and so forth, okay? Here there's a very, very important assumption that is, these points are independent, okay? What does it mean? I mean, the noise that I have here, okay? The value that I draw from this random value here is independent from one point to the next. Okay, so they are said to be independent. And remember probability, when you have independent processes, independent draws, how do you calculate a probability of independent variables? You just multiply them together. Yeah. Okay. So the probability of all of the data points given your model and the parameters is just the product of the probability of each point, yeah? But the probability of each point is just the probability of a normal distribution, okay? That is like this, right? So 1 over the constant and yi minus f of xi squared, okay? Okay, and then when I do the product of all of this stuff here for each point, so I have a product of several exponentials, yeah? So what happens with a product of exponentials? I have the sum of the exponential of the sum, yeah? And then what I have is then the exponential of the sum of what? The squares of the differences. Yeah, so what I want to do is I want to maximize the likelihood. Take the value, the parameters A and B such that this is the maximum likelihood possible. So to maximize this function here, I want to minimize the sum here because there's a minus here. Yeah, so I have to minimize the sum of the squares. Yeah, so least squares is nothing more than maximum likelihood when you have a normal error for your measurement error. Yeah, so it's kind of a very specific thing from a general idea. Yeah, so what you can do from this? Okay, so you can use different models for error. Okay, so instead of for instance, if you are talking about populations, okay, for like epidemic time series. Gaussian errors are kind of fun, especially if you're close to, you have very few individuals. Your Gaussian error, it may allow for negative populations, and that's weird, right? So a model that allows for negative populations is kind of funny, right? So usually you use something like binomial or some other, or negative binomial. You have other error models that are more appropriate because they only allow positive values, for instance. Okay? But if you do that, then you can still use maximum likelihood, but you can no longer use least squares. Okay? Yeah, because other error models don't lead to least squares. Okay? This is tied to two main assumptions: independence of data points and measurement error only at each data point being normal. Okay? So far, so good, people. Yeah? Okay, so let's try something a little bit harder now, right? So just to see that, okay, this is a linear function that we tried before. Let's do now something with a non-linear function. Okay, but this doesn't change anything, okay, because I have here a function that is a sine, okay? So I have these two parameters here, 2.5 and 1.2, and I just sum a random noise later, and I have a data set that looks like this, okay? How do I fit this? well, I have my model here, and here is, I know exactly what model to use, right? Because I, I just wrote this before, right? So I have A and B here, and the process is pretty much the same. I have A and B free. I call this curve fit here with this sign function with the data points X and Y, okay? And after I run this, it gives me back the coefficients, okay? And the coefficients here is 2.2 and 1.16. That is pretty close, right? It's pretty close to the ones I use it here. And you see from the plot that it's, yeah, it's kind of works, right? So, but the variability here is quite high, yeah? Okay, so it's another example. So for maximum likelihood, your function, the function you're fitting, right? So this function here, the sign function here, it doesn't have to be linear, right? It doesn't have to be linear, okay? It may be nonlinear, it can be whatever you want, okay? I think the basic methods for least squares fitting that we learn, I don't know, in numerical calculus, only work with a very limited set of functions, but you can use curve fit to fit any nonlinear model whatsoever, okay? Okay. Okay, now let's do something more interesting, okay? Because so far, we're just fitting points to functions, okay? But now we want to move on to look at solutions of models, solutions of differential equations, okay? Okay? Okay, of course, solutions to differential equations are just functions, yeah? They're just functions. So you can treat the solution of a differential equation just as a function, yeah? Okay, and then you take that solution and compare to the data. Yeah? Will this work? Or are we being too optimistic? I don't know. So here I have, I will use some logical model on population of protozoa. This is a Paramecium aurelia. This, I think, is a last L data set of growth of protozoa in the lab, okay? I think these are very large protozoa that you can see on the microscope, you know, because people did this in the 40s, I guess, 30s or 40s, yeah? So when I say classic, it's classic. It's like almost 100 years old, okay? Okay, and this clearly shows a pattern of going up and then stabilizing, right? So I'm going to fit something that looks like that. That is the logistic equation, okay? That we didn't discuss in this course, but it has this kind of dynamic. It grows exponentially at very low values, and then it saturates close to it saturates at the carrying capacity, okay? Okay, so how do I go about this? So I have to do what? I have to write a function that, given the parameters, will return the values, the predicted values of the data at each of the points in time in this case, okay? So what do? I use our integrator here, ODInt. I write the equation for the logistic equation here. This is all stuff that we are very comfortable with right now, okay? Okay, and now I need a function that does the solution, okay? So I take here the solution, and at which data points, okay? The data points will be the values of t are going to be the observed values of t here, okay? So you see that in this list here, I observe this at point 0, 2, 3, but not at 1, for instance, okay? I observe at these points in time, okay? So I'm going to pass this, the first column here, okay, of the pop array here. The pop is this array, okay? Okay. So this function here has to calculate the solution at those data points with these parameters here, and I will also do something that is very useful in practice, okay? Because you can look at this and say, okay, I know the initial condition, okay? I know that the initial condition is, at the time 0 is 2, okay? 2 protozoa only, yeah? But actually, frequently it is not so clear, okay? So it's, you know, there are 2, but did they just end reproducing, or or they are about to become 3. You know, you don't know exactly. You see, there is some variation here. Even if you think you know the number, there's some room for variation in this number. Yes or no? Right. So I will also leave a third parameter here that is actually the initial condition. So the initial condition can be taken also as a parameter, okay? Because it also helps to define the solution, okay? So I have here R, K, and the initial value of the population. And then the ODE will use these values of R, K, and initial population, okay? And now this ODE is not going to return a single array, it's going to return an array with 2 I should probably make this later to show, right? But it is going to give me actually an array with a single column, but I want to take just the single column. I want a 1G array and not a 2G array, so I take just the first column here, okay? Okay, and now I use, with this logistic solve here, I use my curve fit with this logistic solve and the data, the first column of the data, the X and the Y, okay? When I do this, I get back the parameters and the covariance matrix. Okay, so let me run this. Okay, here it is. So I get the first parameter here is going to be 0.76. That this is R. The K is going to be 543, and the initial condition is 2.5. Okay, so you see the initial condition is pretty close to, of course, to what we had from the data, but it's not exactly 2. You know, and this is what the data in the fitted model looks like, okay? Yeah, looks okay? Yeah, okay. Of course, you see, we are never going to get exactly the data, okay? But this looks reasonable. Okay. Now, first question is, okay, we consider N0 here, okay? Could we just set N0 equals to 2 and that's it? Perhaps, right? So maybe we should try running again, right? Maybe if we have a bit of spare time, we try this. But if we don't, okay, so many of these questions, I think I will leave for you to try later at home, okay? Yeah? Okay, so maybe it didn't matter so much to use or not the initial condition. Okay. The second thing here is that we have a warning here. I don't know if you have seen this kind of stuff when you run your models. This ODE int warning, excess work done, is it familiar to you? Yeah? Yeah, okay. So what does this mean? It means that the numerical integrator, the ODE int, is having trouble solving the equations, okay? Usually this means that either you have something wrong in your model, this is a possibility, right? And then you get stuff like populations going to infinity or minus infinity and everything going wrong. Or sometimes it's that your model is what is called stiff, and then we have to tune a little bit the integration parameters. If you need some help with this in your own work, you can ask me and I can help you, okay? But why does this happen here in the logistic equation that is kind of the easiest equation to solve in the world, okay? How come? The thing is, if we had set R values or K values or even N0 values for negative values, then this model doesn't make sense at all. It goes to minus infinity and so on and so forth, okay? And the curve fit is just, how does it find the best parameters? It tries to explore the parameters. It tries to run for many different sets of parameters. And sometimes it can go into kind of forbidden regions like negative values of K or N0 and so on. And then it's going to give you this kind of warning, okay? Usually you don't have to worry about it, but it's important to know that this can be an issue, okay? Your model takes a lot of time to run because it's trying to run with parameters that don't make any sense biologically, but the computer doesn't know that, okay? So it will try with negative values of initial condition and so on, okay? Okay. Okay. So let's try an epidemiological model right now, okay? Yeah, finally. Okay, epidemiological model. So here, again, it's not just laziness, okay? But I will talk about this later. I took very classical data from this book, actually, from children with influenza in a boarding school in the 70s, okay? So this is, let me show the year first. Yeah. Oop, no. This is just too much information. Sorry. No. Let me just delete this stuff here. So I want to plot just the data first, okay? So let me stop here. Okay, so plus O here. And I just want to plot the data itself, okay? So and maybe with dots, right? Here it is. So this is the data. Okay. So what is this data? This is number number of beds occupied by children, right? This is not new cases, right? Because people get infected, children get infected, they stay in bed until they recover. Yeah? And this is not children that are infected. This is number of beds occupied. Yeah? So if I were to build a very simple model, what would be the correspondence? For instance, think of an SIR model. What is the correspondence here between this data and your model? This is the first question I have to ask, okay? Because otherwise you're kind of comparing apples to oranges, okay? Yeah, so what is the relationship between an SIR model, the variables in an SIR model, and this kind of data, data on number of beds occupied? No idea? No, really? No, or you're just too shy today, or too tired? Really no idea. Yeah, infected people, right? Because someone that's infected, and then it has to stay in bed until it recovers, and when it recovers, it gets out of bed. And then, yeah, so this is should be pretty closely related to infected individuals. Yes or no? Objections? Okay, so we are going to do what here? I'm going to try to fit an SIR model comparing number of infected individuals with this data. Okay? Okay, so we have some more information here. So recovery time was in the range of 5 to 7 days. I had the total population, the number of people in this U of 763. And we know that at some point, more than 500 of them became ill, okay? Okay, so I have this, the data, and what do I do, okay? I write my SIR model here, yeah? Nothing new about this. And I have to do the stuff of, okay, I will fix gamma, okay? So if I have a recovery rate of about 5 to 7 days, I'll just put gamma equals to 1/5, okay? And my time is already measured in days, okay? Okay, and at the initial point here, I have 3 individuals infected. I can use maybe an initial condition of 3 people infected, but I will once again do the stuff of leaving I0 arbitrary, okay? Yeah? Okay. So with that, I solve the SIR model here, okay, with n, the total population minus I0, and 0 over at the beginning. The time will be the times here in the data set. And then I have beta and gamma, okay? But beta I'm fitting, and gamma I'm not fitting, okay? Gamma is fitted here, okay? It's not passed here. You see, so I'm not fitting gamma. I'm only fitting beta and the initial value of infected, okay? And here I take what? I take the second column, okay? That is the number of infected individuals. This is what I'm going to compare to the data, okay? Okay, then all my function curve fit. And here there's a special parameter that I included here, this P0, that is my initial guess, okay? So my initial guess for the parameters are beta, and I0. So I put 1 and 2 here, okay? So I guess that beta is going to be close to 1, and I0 is going to be close to, let's put 3 here, okay? Because this is what is in the first data set, the data point here, okay? And then I run this, okay? Well. So what do you think of this fitting here? From a range of from bad to extremely bad. Yeah? Bad, right? Terrible. Yeah? Because of course you didn't start with 100 infectious individuals. It doesn't make any sense. Yeah? Okay? But then what is going on? Is my curve fit function broken? Is it giving me nonsense? So could I maybe find something better? So let's try to mess with this a bit, right? So instead of letting the computer do stuff, let's do our stuff by hand, okay? So what I'm going to do is, okay, I'm going to solve the model here, and I'm going to put the parameters by hand here, okay? So I'm going to say the initial condition is going to be with 3 individuals infected, and I'm going to choose the values of beta here, okay? And let's start with a very high value here. So here it is. So if beta very high, does it look bad to you or not? It is bad, but it doesn't look as bad as this, right? But from the point of view of least squares, this is better than this. Yeah, because here you have very, very large distances in these points here, you see? And here, even in the worst points, this is not so much as these distances here. You see? So it's kind of weird, because visually we think of something in a certain way, but the computer doesn't understand it in that way. You know, it tries to minimize the squares. It really takes it seriously, okay? Even for this looks better as a shape of the epidemic, okay? The fitting is not actually better, okay? So, but, well, I put a large beta, right? So what if we decrease beta, okay? Okay, so let me go back to 1.5. And this is slightly better, right? But I'm still having very large deviance from data here. And if I go down here, I have this stuff. And now you see that as I decrease beta, everything shifts to the right. And then I start to have very large deviances over here. And this model provides a worse fit in terms of least squares than what we had up there. You see? So there's actually no value of beta of beta with this value of R0 that gives you something better than this in terms of least squares. Okay? So maybe we shouldn't have allowed it to fit I0. Okay? Maybe we should have gone with this actually, okay, and allowed it to fit only beta, okay? Maybe this would be for the best, yeah? Let's see. Oops. Oh, okay, sorry. This is just -3 and 3 here, okay. Yeah, and this is the best fit that it gets, okay? With coefficient of beta of 1.6, okay? So if we don't allow it to fit the initial condition, we actually find something that is looking with your eyes, right? It looks better than in the previous scenario, but it's still very bad. Yeah. So why is it so bad? Well, any guesses? Sorry? The assumptions that we made, but well, probably SIR model is too simple for that, right? Because you see, if we try to decrease beta, then all of the curve shifts to the right, weakly. Yeah, so maybe we should have included something like, I don't know, incubation phase or something like that, right? So, yeah, we have to improve our model, okay? This is a sign of maybe there's something important that you didn't include, okay? But you see that it's fitting models is hard because you don't know in which way you are getting things wrong. You may try different stuff, but the fit itself doesn't tell you what's wrong. You know, it tells you just there's something missing. What? No idea. Yeah. Okay. Okay. So this is kind of bleak. Yeah. Okay. Let's try some other example. Okay. Some other example. Okay. Okay, so this second example is an epidemic of measles in Niger, in Niamey, okay? And now this is new weekly cases reported in this outbreak. Actually, I think I should update this to, Brazil 2018-19, okay? Because there are recent measles epidemics, okay? But anyway, this is the data we have right now. And let me see. Here I plotted just the data first. Okay, so this is what the data looks like. Okay, so it's a bit noisy over here, but it's clearly an epidemic. Yeah, from and this is weekly. Okay, this is weekly. Okay, okay. So once again, I'm going to try to fit an SIR model. Okay, I know I should have learned that lesson from before, but let's once again try to fit an SIR model, okay? Now, this is new reported cases per week, okay? So what do we compare our models to from an SIR model? We have to do that stuff of computing new cases per week, yeah? We can't just compare it to susceptibles or infected or whatever, yeah? We have to compare it to new cases per week, okay? So once again, we have the times here. I think here, this is 42 weeks. So I'm putting my times AO here. 1 to 32 is 32 weeks. So my times AO here is in weeks, okay? I have a gamma here that is, I think this is ovary rate of about, infectious period about 9 days. So 9 days is 9/7 weeks, okay? So this is why there's a 7 over here, okay? But let's look at the rest of the stuff here, okay? So this is total population of Niamey, but you also have this stuff here, okay? Measles. Well, many people are vaccinated, yeah? Many people are vaccinated. So you cannot say once again that initial population is like everyone is susceptible and that's it, right? You can't. So what do? You have to include in your model the fact that in the initial population you have a large proportion of recovered people, like there are people that are already immune to the disease. Yes. Do we know how much of the population is already immune? No, we don't, okay? We don't have this data. So we'll have to fit it somehow, okay? And finally, we can use the fact that we know R0 for measles. We have some estimates for R0 between 12 and 18, okay? So maybe we try to use this to fit beta, or maybe we try to fit beta, I don't know, okay? Okay, so let's do it. let's go. So this total population, this is gamma that I'm going to fix it. This is our SIR model once again, okay? And this is what we're going to, how we are going to generate the data. Okay, so what we need to generate this data? The data points, the time points, beta, sorry. R0 here is not the R0, is not R0, is not basic reproduction number. It's initial number of recovered individuals. Yeah, so yeah, so let me, when you forget stuff like that, R0 is initial number of recovered. Yeah, so when you document your code, you have to remember the main target for documentation is your future self, okay? Yeah, your future self needs to know and remember what you're thinking, yeah? Okay. Okay, and I0, of course, is the initial number of infected individuals, okay? So my initial condition is going to be the total population minus R0 and I0 for susceptibles and I0, R0 for the other two, yeah? And now, yeah, this is a little bit funny, okay? So what is this? Okay, so remember that when I look at, I'm going to do, I ship this. Let me just do it for the other one. Right? So I solve the equation, and then I have to do the stuff about the new cases. Yeah, the new cases. I take the susceptibles, that is all on 0, and I take the ones from this week minus the ones from the next week, okay? Because it's the reverse sign and so on, okay? Just as we did before, okay? But this leaves us with one less point than the number of times, yeah? Yes or no? Right, so if I have, I don't know, 30 weeks in the simulation, this will leave us with only 29 weeks of data, yeah? But the T here is the number of weeks in the data set. So what do I have to do? I have to start the simulation 1 week before the data starts, yeah? Because then I have the new cases in the first week, yeah? So I have the data here, I have here week 1. But how do I compute from my model the number of new cases in week 1? I have to start the simulation at time 0, yeah? Clear? So here inside here, I do this trick. I have the time t is not only the original time t, the data points, is the time t, but with the initial point being the first point minus 1 week. Yeah? So far so good? Yeah. And then I just return this vector here of new cases, okay? And this is what's going to be compared to the data. And here it is, okay? Okay. And yeah, kind of okay. Yeah. Well, after the previous one, this looks great, right? So yeah. Okay. So, but the interesting thing here is that we have not only this curve here, but we also can look at the parameters that we found. Yeah. So the parameters that we found was, so the order is beta, R0, I0, okay? So beta is the param 0. If we divide the param 0 by gamma, we have the estimated R0 from this data, yeah? This is for measles. We are expecting to be between 12 and 18, yeah? Well, this is kind of high, even for measles, yeah? So what do we think about our fitting right now? You see, even though we got a good agreement between data and the epidemic curve, we got this at the cost of having parameters that made no sense, okay? Because measles doesn't have an R060, okay? Yes. Yeah, but it's already included here, yeah, because I fitted the initial number of recovered as well, right?
But the expression itself, beta over gamma, it's considering that S0 is
Close to 1, close to the whole population, yeah, but
is even. So if we put the n minus r0 divided by m and multiplied by beta over gamma.
yeah, I guess what you're saying is okay, but well, R0 is only for when the whole population is susceptible, and here we don't have the whole population susceptible. We just calculated. Let's calculate this also. Yeah, just yeah. So the problem 1 was the initial number of what was the order? R and then I. So the first parameter is the initial number of infectious individuals over the whole population. It means that I started with a very small incidence. Oops. But let's see the initial number of recovered individuals. Yeah. So this is, so initially, 97% of the population is immune. Yeah. So this is what our model is telling. This is what this fitting is telling us, right? So this is in a word, right? So 97% of the population. So you see what the fitting is doing, but because what you're saying is okay, but this is R0 is only for whole population susceptible. But here, since we are leaving the immune individual, the proportion of immune individuals free, it's kind of funny because we can either have few people immune and a low value for transmissibility, or we can have almost everyone immune, but a very high transmissibility. And these two things kind of cancel each other out. Yeah? You see what I mean, people? Like, we can have this shape here, okay, this shape here, because this is number of reported cases. So this is thousands of cases, okay? We have two ways of arriving at that point, right? So we can either have very few people immune, like, I don't know, only half of the people is immune, very few people have taken the vaccine, but then we use a beta for measles that is actually low because measles has an R0 12 to 18, right? Or we can have kind of the same result. Yeah, let's try to do something interesting over here, right? So let's try to fix the value of beta. Yeah, let's try to fix the value of beta. So instead of having beta being anything, right? We say that beta here. Maybe let me not mess with this. Let's make an OPI. Okay, let's make an OPI down here. Okay, so now instead of beta here, oops, I will put beta over here, and I'll say that beta is, well, it should be R0. Let's say that R0 is on the low side. Okay, so this is 12 times gamma, yeah? Times gamma. And gamma is just gamma, yeah, over here. Okay? And then I don't fit this. Okay, I'm not fitting beta anymore. Okay, I'm fitting beta because I know gamma and I think I know R0. Okay? Yeah, so I fitted beta, so I have one less parameter to fit, and I have to change it here because now I just have one less parameter here. Okay. I think this is going to work. Hope so. So you see, the fit got substantially worse. Yeah, substantially worse. Okay, but then if you now look at the parameter for recovered, okay, the number of recovered individuals that it estimates is only 90%, no longer 97%. Okay, so in order to get a better fit, it's saying that there's less immune people than before. okay? Maybe we can go to the higher range of R0, okay, 18, okay? If we do this, we get this other fit here, okay, that is a bit better than before, yeah, than the one that I just showed you. Yeah, and now it's going to say what? It's going to say that the number of immune people is 93%. Okay, you see that in this case there's an issue here, that is the initial number of the initial number of immune people is very strongly coupled with beta. Yeah, so these parameters are not independent, right? And when you try to fit both of them together, okay, sometimes you get this stuff where, well, it puts both of them at very high values, even for parameters that are not really reasonable, you see? Yeah, so you got a very good fit up here, very good fit up here, but this is at the cost of finding parameters that are unreasonable, okay? We don't expect R0 to be 60, okay? Yeah? So you see, fitting is complicated because even when it looks like it's going well, you have to be critical. You have to think critically about the parameters that you're getting from the fit. Sometimes they may make no sense from the realistic perspective, yeah? Okay, so you have to have some idea before, yes?
And when we have two parameters that have some correlation, what can we do to avoid this?
If it is perfect 100% correlation, you fit just one of them, right? But in this case, for instance, they're not perfectly correlated, right? They're not like equivalent. You see that when I fit beta at different values, I get better or worse fits, you know, so they're not perfectly correlated, you know, so there's not much you can do, right? So you have to live with that, okay? But you have to be aware that this phenomenon may occur, that the best fit ends up being for extreme values for both that are actually not realistic, you know, so it's something to be aware, but you can include bounds, okay? So I think I left some notation here that you can include bounds in curve fit, okay, or fit accepts boundaries, okay, saying you can tell it should say, oh, the minimum and maximum values that you're going to try is in this region here, okay? But yeah, that's it, okay? That's nothing much better. Okay, people, questions? We are already late, right? But questions. So the best part of the class, right? So is now, but it's already. Are you too hungry or not so much? Can we go over a bit? Because this is, I think, the best part, right? So you see that I painted a pretty bleak thing here because you see everything failed, yeah, except for the bacteria growing in the lab. Okay, everything else failed for our epidemic models, right? Why? Well, we're using models that are too simple. Yeah, of course, this is one situation, but also you have many issues, right? Many issues. So this is really important to think about, right? So the first issue that is huge is you have an epidemic, okay? You have an epidemic. You have a certain number of infectious individuals, new cases, in this week, okay? And then the next week you have another number of new cases, yeah? Are these two numbers unrelated? Are they independent of each other? If, for instance, something weird happens, like there's a party that everyone goes and there's a peak in infections in this first week here, will it change the trajectory of the disease for the following weeks or not? Yes, right? Yes, it's going to change the trajectory. But if you're using least squares and so on, you're assuming that this is not the case, that this peak here in the previous week was just measurement error, okay? And this is, so there's a strong violation of your model assumptions, okay? So least squares is not good for time series where you have a process that at each time step it depends on the previous value, okay? So this is why I said, okay, we can have, so what would be the better way to include this, okay? We have to fit each step of the model separately, okay? We have to say our model predicts these new ages from this point to the next point, and then it has to make a new prediction from this point to the next point, considering what you have observed in the previous point, and not the whole curve at once, yeah? Because if you have some random noise that is a process noise in one point, it's going to affect the whole rest of the curve. You cannot just ignore that, okay? So this is a big issue, yes? Sorry?
This isn't the case of overfitting the
Sorry?
This isn't the case of overfitting the data?
No, this is not the case of overfitting the data because you won't have one parameter per time step. You see, because what you're saying, I'm not going to say, oh, I'm going to fit beta for time step 1, for time step 2, for time step 2. No, but you're going to consider that that your beta, it doesn't generate a single curve. It generates a series of predictions for the first time step, a series of predictions for the second time step, and so on. So you have to include process noise. And process noise means that your model can no longer be deterministic. You need to include process noise into your model. So you have to go from an ordinary differential equation to a stochastic equation or a stochastic differential equation that has noise. And then you're going to fit the model parameters and the noise of your model, of the process noise as well. You see? But it's not overfitting because you're not going to fit, I don't know, if you have 30 points of data, you're not going to fit 30 parameters. You're going to fit a single beta for the whole process, but taking into account each step separately. You see what I mean? Or it's kind of complicated, right? But yeah, we can discuss later. But the state of the art is this kind of stuff, okay? It's not, we cannot just assume that the data points are independent observations of the process, okay? And also, yeah, what I just said, errors can also be due to process variability. This is stuff of, okay, there was a party, there's a peaking of infections, and it changes the whole curve, okay? Okay. Another problem is identifiability of parameters, okay? So this is what he was just asking about. If I have 100% correlation between two parameters, it means that I cannot identify, I cannot parameterize, I cannot fit the two of them at once, okay? Because if they are exactly this, they're two unrelated, okay? If you fit one, you get the other, and vice versa, okay? So you cannot fit them both at the same time, okay? This is kind of the easy case. When two parameters are perfectly unrelated, usually you kind of can detect it more or less easily, okay? The real issue is when two parameters determine a third, okay? And then things get messy, okay? This is not super common, but it's common enough to be an issue, okay? Finally, these maximum likelihood methods, okay, that I just showed you about, okay, they don't incorporate other sources of information. So for instance, I cannot tell you, I can tell you something like, okay, I know that my R0 in the previous example is between 12 and 18, and I can tell the maximum likelihood estimator to stay in these bounds, okay? It will find the best value within these bounds. But I cannot tell it that you already have a previous estimation with a certain distribution and so on and so forth. So I am very limited to what previous information I can include in this estimation, okay? So if I want to include previous information in terms of distribution of parameters and so on, I do need Bayesian methods, okay? Bayesian methods, yeah? That I won't even say what they are, okay? Okay. Finally, some less general, more technical issues is that these likelihood functions, okay, these they may have many local peaks. That means by function curve fit, it may have issues finding what are the best parameters, okay? You may think it found one, but actually there's some other one that it missed it because, you have to think in terms of parameter space, right? So there's this R that is the residuals, right? So the difference of the sum of the least squares and so on, or the sum of the squares. And you think of this in terms as a function of the parameters. You have a peak over here, and it finds this peak. But there was some other peak somewhere else that it didn't find, and it goes to the lower peak instead of the higher peak. And this can be technically challenged, especially when you have more parameters, right? So when you go from 2 to 4 or 5 parameters, it's already a big issue. Okay? And finally, model fitting may not converge. Okay? It may even not even find any peak. So this happens also. Okay. Okay, people. Thank you for your patience. We can. I don't know. This is very conceptual stuff, right? But unfortunately, should really go deep into these issues, I would need more than an extra lecture, maybe a whole extra course, But I think it's important to have an idea of how this stuff works, what are the main issues, and yeah, I hope it's useful. Yeah? Okay, and we can discuss more tomorrow and off and so on, okay? So thank you for the patience. And now lunch, yeah, finally.